record the class. All right, perfect. Morning, sir. It's morning somewhere. All right, so first things first, we test on Thursday. Test one is Thursday. Everyone been able to access practice exam? You guys checked the practice exam. That was from the practice exam. You checked it also. Awesome, perfect. So hopefully Derek has also attempted the practice exam. Test is on Thursday, and basically thinking probably maybe 25 problems or maybe 10 problems, 10 to 25 problems. Big range. Yeah, it's a really big range. Depends. I'm probably gonna like short it to maybe somewhere between 10 and 25. These are some of the questions that I get asked are like straightforward questions. Hey, you cross product with this. Right. And that's a nice question.
That is nice. I appreciate those questions.
I think everyone, I would appreciate grading those questions. My biggest problem sometimes when I grade a bunch of stuff and I look at it and I'm like, what were they thinking? And yeah. Well, it's like the quiz. It's like the quiz.
Did you grade it?
Do I have it ready for you guys right now? No, I did great. I'm gonna probably post up the grades on Canvas, but usually when it comes to a quiz, I don't really care for a quiz, if that makes any sense. So like, I'm probably gonna drop like the lowest, like two or three quizzes. And then,
You did that bad?
no, you're specific.
I'm surprised.
I'm kidding. No. It wasn't that bad. So yeah, I'll probably drop like the lowest 2 or 3 quizzes, and then
Over the course of
the entire semester.
got it. Okay.
And then for tests, I don't drop tests.
Okay.
Yeah.
So everyone counts.
Yes.
Every test counts.
Mhm.
Alright.
That's why I want you guys to study. That's why I made sure I had that practice exam ready for you. I think I posted it like Friday night or something.
Yeah, it's been on.
Yeah. Alright, so, yeah, so that's gonna be on Thursday, we're gonna do maybe 10, 25 problems, roughly around that range. Don't stress too much on it. It should be a fairly easy exam. One you should stress about will be exam number 3. That's when it's going to be good. That's what we're doing, like Green's theorem or something like that. And that requires a lot of messing. When you're doing double and triple integrals, you have to select the correct integral to attack first. If you attack it the wrong way, you could spend like 10 to 15 minutes working on one integral and you realize, wait, I went the wrong way, I have to start from the beginning. So that's when it becomes okay, did I effectively step? So very soon, we're hopefully by tonight, we're going to begin limits and derivatives and integrals. When you do derivatives or you do a limit of a vector value function, you do it component wise, which is a good thing. So you'll take the derivative of the x component, the derivative of the y component, and the derivative of the z component. But the thing is, I'm going to expect that you guys know how to take derivatives. I'm going to expect that you guys know how to take integrals. I'm going to expect that you guys know how to take limits as well. But if you don't remember that, message me, tell me, hey, I don't remember this. So maybe we can set up a Zoom meeting with Quayman to figure out what you're lacking. Just because if you don't know how to do it, then the rest of this class is going to seem like a nightmare. Because when we're doing double integrals, and you can't take the first integral, then you're going to suffer. And I don't want anyone to suffer in this class. Unless it's Chase. Okay. All right. So what we're trying to set up is this idea. What we're trying to do is this. We have this 3D world. And within this 3D world, we're going to have our X, our Y, and our Z axis. And what we're going to do is we're going to start looking at actual planes in this world. And on these planes, we're going to look at specific points on these planes. And we're going to eventually start drawing some nice shapes. One shape that we're going to look at very much in particular is this shape. If we just have the X and Y world, we can have maybe a specific circle. And in the X and Y world, we'll have a nice circle, but if we take it and we put it in the 3D world, it might be a different shape. It might end up being something like that. A nice line curve. But if you look at it sandwiched, it'll look like a circle. But we have to make it, we'll say, you have to understand why these two are going to be the same, but different at the same time. In the 2D world, we're like, oh, we recognize it. But in the 3D world, it's not that. Definitely not that. If you think about it, if you take this 3D shape and look at it from above, it's going to look like a circle. It's going to look like an ellipse. Or it's going to look like a purple. It'll look like an ellipse or a circle. So we have to understand what's going to happen in this world. One easy way to understand that is by using our dot products or cross products and all that other fun stuff that we've been doing for the past. Well, we've been together for almost a month, right? Probably longer than a month, right? Yeah. Also, I'm gonna make this comment, just because it happened in my other class. It was extremely hilarious. So, and I know you guys aren't gonna do this because you guys are dedicated. But the other class, they had a test yesterday. And someone said, Professor, I haven't gotten the program. How am I gonna take the test? And we've been together for how long already? It's been at least a month and a week, right? But they had a month and a week to get the program, and they were like, "Oh, I can't take the exam because I didn't buy the program." And the only thing I could say was, "Well, you had 2 weeks to get the free trial to make arrangements to get the program. I apologize if you wasn't able to, but at this point in time, there's nothing that I can do for you. You would have reached out to me maybe within 2 weeks that you had the free trial. Maybe I could have made some arrangements with the bookstore or something. But now that you're reaching out to me on the day of the test, there's nothing I can do." What I'm saying is, thank you guys for being dedicated to your work. Alright, so last thing we were ending with last week was polar vortex, if I remember correctly. We were rotating R values or negating the R values and negating the theta value, which is basically the rotation in the opposite direction. All right, so looking at this, so let's start probably with a warm-up exercise. Remain open. Okay. So it's gonna be 5. I'm not sure if I gave that to you guys.
I'm not sure.
Probably not, right? Okay,
I don't remember.
me neither. It was just last week, but I could barely remember what happened yesterday. All right. So I want you to find a negative value for this and a negative theta.
Isn't data already negative?
Oh, sorry. What's the opposite of negative again?
Positive.
I mean, positive. Theta. There you go. Sorry. I think by the time November comes, I'm gonna walk in with a forklift or a wheelchair. I'm gonna access you guys also. Do you want test to be a Pearson? Or do you want a paper exam?
If it's on Pearson, we actually would have to like submit our work like separately, or
Oh, no, you just take it here and then you just give me the work.
how would we take it here?
Do you guys have laptops or no?
Yeah. I mean, we all do that.
Yeah.
I mean, I say answer for the whole class there. I do, but
Alright, who does not have a laptop? Okay, we could do it like that if you like, or we could do a paper exam. One thing is, I'm skeptical because when I made the paper exam for the class I'm giving tonight, I basically have to pull teeth to get this done.
gotcha.
Yes, it was painful. If I could just put a Pearson, it'll be a lot easier for the night classes. They forget about us so much.
Pearson's, I'm cool with Pearson.
Alright.
As long as it's-
So it's more closer to home.
I'm sorry?
So are you like using Pearson to do the test on Pearson?
So what I could, I could probably just take questions from Pearson.
All right, let's do Pearson.
And you guys like the questions on Pearson, right?
I do.
Okay, we could probably just take the questions straight from Pearson, so the question straight from my head. All right, I like that too. All right, so we'll keep this first test with Pearson. Third test might be from my head.
Gotcha.
Second test, we'll keep it up there. All right, who wants to do this bad going board?
I got it.
Oh, you guys didn't do it. I was talking too much, right? I think I'm Joe. Okay, which one's Joe? Which one's Joey again?
I can be Joe. He's Joe.
Okay. All right, so Joe. Yeah. Throw you on the board. Perfect. How did you get 3 pi over 4?
Got 3 pi over 4 by taking like, you can just add, what is that, pi to that to get the opposite angle. And then go backwards with the 5.
Perfect. So now who wants to do the hard part? The hard part is to graph it. Who wants to graph? Oh, both. You can handle it, or is it too? You got this, Joey?
Yeah, I can do it.
All right.
Break the losing record. Battle ready.
Last week,
I blew it, Professor.
no, you did good, you did
So do you want me to just -5 3 pi over 4?
good. Mm-hmm.
So I do this. -5 3 pi 4.
Okay, and you could like, Oh, yeah, just label it, that's perfect.
Do you want me to label it?
Yeah, just label it, there we go. That makes me feel a lot better. Perfect, excellent, any questions about that? Easy stuff, right? This is something we definitely want to learn test, and I think Kirsten has easy questions like this. Okay, so let me try some like easy questions like this. No, sorry?
Isn't it 5?
Oh, no, you grabbed this guy.
Oh, yeah, sorry, I'm showing you how to graph. It is technically.
It's the same.
It's
It's all the same, yeah.
It's the same thing, but
What's Chief doesn't see that, do you not see that, Chief? These two are equivalent. Oh, you see that, okay, sure, sure. Did you question it? You're like, hey, what? Okay, that's fine. Okay. So what we're gonna look at also is this. Let's say we do this. And let's say we do 1. And we'll say just sketch the reading. So just sketch the reading. How was this region going to look?
Already saying it's 2 different problems.
Oh, these are 2 different problems. Sorry. Maybe I should make that clear. There we go.
just from the circle,
Not just a circle, right?
this is just a circle.
Are we still working in 2D, guys?
Yes. We have to build up to 3D. Because 3D, what we're going to do is we're going to have to bring in a height. And if we bring in a height, then we're going to have not just a circle, but a nice sphere. That's where we're going to get our nice cylinders and all this cool stuff. So this is just basically a circle at 5, right? Going around, right? We make sure that we have dotted lines because the boundaries are not included, correct?
Yep.
So if everything less than 5, so it means it's going to be everything in the center, right? And now the next one is basically a what?
Donut.
Donut, right?
Solid odds.
Oh yeah, this is included. My apologies. The other thing is I can trace, right?
Right.
Yeah. We'll just include everything on this amazing donut. Okay, so then what about? What if I do this? What if I say theta is between pi over 2 and pi? How is that graph going to? Let's see if anyone. So where is pi over 2 in this theta? At 90, right? So we know it's going to be right here at pi over 2. And now where's pi? Right, it's right there, right? Pi. So we're going to include everything in this amazing quadrant, right? But if that's the only thing we're going to include, We're gonna include something else, yes, sir. The opposite of the quadrant as well. We're gonna also include this guy as well. Ringing a bell? Because
Why
we're
is
gonna,
that? Oh, because you could have a negative R.
exactly right. Because we can have a negative R. And this one, what we can say is R is kind of free. But we have to include those negative values as well. So what we're basically gonna get is almost something close to a half plane. It's not really a half plane, but it's a half plane. Like you just take this half and this half, it's kind of like a half. It's just shooting out in two different directions. Good job. Any questions about that? It's all ringing a bell from trig. Probably some of you took trig back in high school, maybe 2 years ago. Or three, give or take, right? Did you go to a public high school?
I did not,
You went to private school? Homeschool. Okay, all right. I gotta ask, how was that?
it's good, it's good.
But, like, did you have friends? I gotta ask.
Yes, I had lots of friends,
Okay.
I was not, lots of friends.
Was it like cyber school or was it just like your parents?
Kind of a mix.
Kind of a mix, okay. So I'm assuming you're
It was
both,
very legit, like I have a diploma and everything.
oh, of course, yeah, because cyber school is now official.
And you can get like diplomas through like the PA, like the state of Pennsylvania.
And I'm assuming you had like a virtual teacher or something, or?
For some classes,
Some
and then some was just like more out of textbook and stuff.
Ugh. I want to say ugh, because I didn't get that experience till I was in college, and I had to read from the textbook.
Yeah, it's not fun.
It's not, except for there's a math textbook, that's what it's, I'm sorry, I read math textbooks for a living. All right. So now, let's say if you want to go to rectangular. Polar, I know you guys remember how to do this. There's a rectangular polar, what do you do? Well, we're just gonna say x is gonna be what? R cosine theta. And y is going to be r sine theta, right? This we know, this is what we believe, this is what we do all the time. We're gonna go from polar to rectangular. And this is just like a mini review. If we have R is basically what? Perfect, excellent. And the other one should be what, theta? What is theta? Well, where you go? I love it here. The official, tan theta.
I would assume it's just X over Y,
Not close, reverse that.
Y over X.
Y over. Okay, and I wrote you guys a little notes, because notes are always the best. Note,
Is that inverse tangent? Or just tangent? I don't remember.
should be just tangent, and when we look for theta, it's inverse tangent. We just want theta, theta is
Right,
right,
okay, yes. Gotcha. Yep, alright, that's ringing a bell.
Alright, the note is, we will not use this too often. On points. We will need this. Later for equations. Make sure I make this notes. And the reason why we're gonna need this later is when we're doing Green's theorem and Stokes' theorem. that's when we're gonna need all this ideas. Because that's when the calculus is easier, when you convert it to polar coordinates. That's when you can actually take the integral in such a beautiful way, it's gonna work out perfectly. Because there'll be some rectangular integrals that will be so hard, you will leave that to me to solve by hand. You guys will change the polar coordinates because it's easier to work with. And also, these ideas are in a really good class that I believe all of you should take. If you're an engineer, even if you're an engineer, differential geometry. I love differential geometry. One of my favorite classes in all of mathematics was differential geometry. This is just basically physics, but for math people. Any questions so far? Stuff you guys already know. If you don't know this, I cry. Like a little baby. Alright, so just to make sure that we're all on the same page again, let's say if I gave you, give an example. I said x is equal to 7, convert to polar coordinate. So it'll take 5 minutes to do that. You guys should be able to do this in a heartbeat. Maybe I'll give you a few problems. The one is y is equal to 3, and 3 is going to be x is equal to 2y squared. We'll put Derek on the board. Oh, he's not here. Now he's gonna watch the recording. Be jealous. So x is equal to 7. So we're gonna say this guy's gonna be what r cosine theta, right? Is equal to 7. No, what do we do after that? Are we done, Professor?
Do you want the R isolated on one side?
Let's see. Well, usually, how does this graph look? When we look at this graph, x is equal to 7, which is basically a
Vertical line.
vertical line.
Oh, right, oh, sorry.
Yeah.
Yeah.
Yeah, 2 is gonna be,
Of course, yes.
yeah, go on, go on. We're gonna have a vertical line, right? X is equal to 7. Also, the best way to also remember it is, it's sort of in the form of y is equal to mx plus b. Sort of, and then you're like, wait, what's in front of the apple? There's 1 there, but there's no y, so yeah. Alright, so we know that x is equal to 7. So. Let's see. So, get you guys to play. What's happening to your house here? Alright, let's suppose that theta is equal to 0. What happens if theta is equal to 0?
Or stay the same.
R stays the same, right? Because there's just gonna be a 1, and then we're gonna have R is equal to 7, right? What's really happening to this graph? We think about it, right? We're looking at R is equal to 7. What is, how does that, like, I can't phrase this question without giving an answer. Yeah, let's look at number 2 as well at the same time. How does the graph of y is equal to 3 look? This one is a horizontal line at 3, right? We know that we're going to have r sine of theta is equal to 3. Maybe this might be a little bit easier for you guys to see. If I say theta is equal to 0, what do I get?
0.
I get 0 on this side, and you say 0 is equal to 3. Now it seems a little fishy to you in a way. Like the same thing here, we're going to have two values where we're going to have something go to 0. But we know that this right here should be our equation based on what we know from basic trinity. What we're seeing is we're seeing these holes. These holes are going to become ever more present when we take these types of graphs and put them where? In 3 dimensions. So we're going to eventually see that we're not going to get these, we're going to get, we'll probably get these amazing shapes when we take them to the 3-dimensional world. It's going to go back to what I was saying before. Well, I was telling you that if I had it in a 2D world, I get this nice circle, right? But what can happen with this circle in a 3D world is we can have basically a slinky. We call it the slinky effect. I call it a slinky effect. I think it's been claimed by the mathematician as well. But it looks like a slinky. But when you look at it directly above, you're going to see, oh wait, it's just a circle. What we're going to see is these holes that we know are going to appear here is that's where it's going to start to become ever so present. So dealing with these holes are going to be what we're going to study throughout this entire course. It's going to be really, really, really fun. And now, I think I got that across to you guys, or did I confuse you? I understand roughly. You just got, you'll see it as we progress. You'll start to see, oh wait, oh this makes sense because of course at some point we're gonna get this ugly idea. At some point we're gonna get these other ideas. Oh, well let's take care of these ideas with our integration. Alright. Keep that on the board again. Alright, And then for number three, how is number three going? What are we going to do? We're going to take r cosine of theta, right? So r cosine of theta is equal to 2 times, what is it, r sine of theta squared. And we'll just basically square this guy, so we'll get equals 2 r squared sine squared of theta is equal to r cosine of theta. We can probably solve for r if we want to, right? Or we can do what? What should we do? Well, you probably divide by r on both sides, right? And we'll get cosine of theta is equal to 2 r sine squared of theta. Maybe we'll probably take 2 sine squared of theta over to the other side. And we'll get r is equal to, we'll just leave it as cosine theta over 2 sine squared of theta. We could probably play around with it some more, but we'll just leave it like that. We're happy with it. This is stuff that you guys should know already. James, are you okay? You hiding? Oh, are you sorry? All right. So. Cylindrical coordinates. So. What we're gonna have is, we'll have a 3D graph like so. We'll have X, Y, and Z. And what we're gonna see is, we're gonna have an R, a theta, and a Z value. Of course, we already know what R and theta are going to be. The R and theta is going to be, well, this is going to be our radius, this is going to be our degrees. But Z itself is just basically giving us some height, some breadth, some depth. So once we do that, we're going to notice we're going to have a nice cylinder in space. And what we're going to do is this. This will be our axis. We're going to have some radius going on there. And then we're going to see that we're going to have some distance from that, which is going to have some theta. What we're going to do is this. We're going to have a height. This is going to be a hard thing for me to draw. And I'll try. Going down like that. Now, what we're going to see is, ooh, now we can see that we begin to rotate this. We're going to get that nice cylinder projecting up. So what we can think of, and we've seen this already, we had this concept of what? Casting a shadow. Anyone remember? Projection. The projections are casting a shadow. And this shadow that we have is going to make our nice cylinder. This is what we're doing right here. We're going to say this. Of course, we know r and theta. That's going to be our polar coordinates. Z, we just know is going to be our height.
So it's kind of like a hybrid between rectangular and oval.
Yes. With that hybrid is going to help us create these nice cylinders. Then what we're going to do at the cylinder coordinates, we're going to talk about spherical coordinates. At the spherical coordinates, we're going to try, because spherical coordinates are hard to visualize. Well, not to visualize, but I should say, hard to draw and stuff, so I definitely will not test you on that, because if I can barely draw it, yeah, I'm not gonna force you to do that. But on your Pearson homework, I think the recent one's spherical coordinates and stuff like that, the Southern one, I think that's due after the test, right?
It's the 24th.
24th. So you guys have time. I think that you'll just like sort of we'll say fudge the homework, if that makes sense. Like you'll look at the picture and it'll give you like a synopsis. Oh, this is probably the equation that's mostly related to this. Those pictures are really hard to draw by hand. It's easier to have a computer program. And what we can do is, as we get progress in class, maybe you guys could bring in your computer, and I can ask Eric if we can get you guys some licenses or some codes for Maple, to draw with Maple. It'll be a lot easier, and you guys can see it, and it's like basically you make it yourself. So hopefully we can get that. Okay. So let's try to think about these pictures. I'm gonna leave this on the board. And the example that we're going to do, it's gonna be fun. For example. Think about the picture. Let's fix a variable and leave two of the three. I think this is going to be a good exercise for you to visualize what's going on. So we're going to say R is equal to 2. And if R is equal to 2, that's one variable that we fixed, plus two others will be anything. So Z is anything, theta is anything, but R is 2. Well, R is 2, that means we have a radius of 2. So how does a radius of 2 look like in just a 3D world? Well, if that's hard to visualize, don't worry. Let's just think about it in terms of X and Y.
These cylindrical coordinates, it's the polar component of it is in the XY plane. Yeah, that makes sense. Yeah.
Okay. And then we'll just add Z to it.
Yep.
So it's just gonna be a radius of 2, has a radius
And
of
the
2.
XY, yeah, this is circle.
This is a circle, right? And now if we bring it into this world, well, we're gonna have a circle. Still, this is our X, this is our Y. And now since this H can be any element shape, we'll call it H. Since Z could be anything, what does that mean?
Just infinite.
Infinite in both directions. And, this is the fun part. This is the fun part. You're visualizing the graph, not the exact graph, but it's a good visualization. And I think this will be these topics will be on your next test. Not going to be on Thursday's test. Because we're just seeing it. I don't want to test you on stuff that I just showed you. Unless you guys want to. Now I'm getting on this. All right. Let's try to give you guys good intuition. Now I'm going to say theta is equal to pi over 2. Which means what? Well, R is going to be anything. And Z is going to be. How does theta equal to pi over 2?
In 2D, would that be a line on the y-axis?
Why?
Because that's what.
It just
Wait,
exactly what it is.
that's-
Just this guy right here, it's just the pi over 2. But if we have negative coordinates, can't we include the ones in the bottom as well? So what we're gonna have is basically an x of maybe flat and then a half.
So we're gonna have like a plane.
Sorta. So what we're gonna have is this guy just going to be that guy right there, but we know we have to include everything in the problem. Then we also know that if it's a vector, can't we just include everything else as well? And so basically like the entirety of the 2D world.
Is it a vector?
So it's, this is gonna be, should I pull
Yeah.
it back there?
All of those lines are pi over 2 with respect to the x-axis, so it makes sense that.
Right,
Yeah,
that makes sense, I'm just thinking, yeah, if it's defined as a vector, that would be the case, it could be anywhere.
Even if not, because theta is defined as the angle between the x-axis and, you know what I mean?
Yeah, it could be.
Yeah. Even if you don't think of it as vectors, they still all have this angle from the x-axis.
now, let's try to visualize it as a 3D shape. So how is that gonna look in 3D? Actually, this might be easier if I just do this. So having it look like a corner. Why not make extra axis? I think of it like that. Now this is just going to be slices along the x and y plane. Oh, the x, hold on, we'll call this this guy x, we'll call him y, and we'll call him z.
I don't get how that works. How is theta defined? Is theta defined in relation to x and y, or x and z, or y and z? That logic, I guess, if theta was anything, it would just be a sphere, right?
Mm-hmm. Yeah, I think close. That's
An infinite sphere.
I mean, the z-axis could still be that angle.
That's something that's going to be defined. Okay. I mean, I don't want to think of it as an infinite sphere. Want to think of it like
What is the
not
angle?
a plane.
What?
It's not gonna be a plane. And it won't be an infinite space. Think of it like an infinite disk.
I'm not picturing that. How is the angle pi over 2 defined? Is it defined in relation to x and y or all three?
It should be defined, we defined it before as x and y.
Right. So shouldn't it be all like the arrows would be pointing towards the y axis?
Maybe they just switch these axes. Let's see. No, it still doesn't make sense if I switch those axes. I make this y, make that z.
Yeah, then you're not,
I mean, yeah, I think that.
Alright, let's move on to the next one. This one,
so
We
if you just look at it in the XY. In the XY plane, it is the entire XY plane, okay, and then the height can be anything, so it just becomes 3D
yes,
space entirely, right?
it should just be everything. So it should be the entire 3D world. The best way to visualize this would be if I show you guys on page. That would be the best way. Alright. Next one, so the next one, you're gonna be able to see it perfect. We're gonna say z is equal to 1. We're gonna say, that's gonna mean r is anything. And theta is anything. And I know you guys can visualize this one perfect. The one before is a little yucky, but this one is gonna be better. What makes it better is this. What does z equal to 1 mean? Well, it has a height of 1, which means we're gonna have what? An entire plane. It's gonna have a height of 1, and the
And all
entire plane, yeah. I probably drew it wrong. Because it was- No, wait, yeah, it should just be like a level. I think of it like a, that projector right there. Next to the wall. And I'll take that projector and make it infinite in this direction. That's exactly what it'll be. Hopefully that makes sense. 'Cause it's gonna be like, it's gonna be like an entire level, like an entire floor. Like right there.
Just to infinite
Exactly.
and in all directions.
In all directions, because R can be anything, and theta can be.
I can see that.
Yeah, the one before is hard to see, but once if we get permission from Maple, it'll be perfect. Or do you guys already have Maple? Alright. Now, the next thing we're going to talk about is spherical quirks. Now, once you hear spherical, the first thing that should pop into your head is a sphere, right? But if you remember correctly, remember back when you guys were taking pre-cal, some of us were home with mom and dad. Okay, but yes. When we were taking that pre-cal, what did we do? Well, the first thing we said is, oh, the first thing we talked about was a line. No, first thing we said was a point, right? After a point, we say a line. After a line, we don't talk about a plane because we're in 2D world, where we can say probably the entire XY plane. After that, we start talking about curves, or line curves, or line segments, or stuff of that nature, right? And after that, we say, oh, what about a circle? After we talk about a circle, what else do we talk about? Well, if we have a circle, and that's a special case of a ellipse. if we have an ellipse, we can also have a hyperbola. And those have specific formulas. What we're gonna do is we're gonna say, okay, now we have these specific formulas. We need to say to ourselves, how do we bring it into 3D world? Because now we have to do the same thing. Well, the first thing we did was we talked about a point. How did we talk about a point? We vectorized that point. We took that point and we said, oh, well, we have a point. It's just a nice bracket vector or something like that. Or an actual point with this, a point like this. 3, 2, 1. And after that, we talked about a line. When we talked about a line, we said, okay, let's take that specific point and add it to what? Well, we added to a specific linear combination of all those points in one line times a specific vector. And then we spoke about this in terms of a line segment. We said, okay, now we're going to restrict it to just 0 and 1. Actually, I think I like Brian's notation better. I think that's more student friendly. And it gave us our line segment. And then we said, well, if we want a plane, we do the same exact thing. We still look at that same formula. And we just make it into a plane. Now we're going to say to ourselves, okay, we're going to do the same thing for a circle. Well, we need to remember the formula of the circle. Well, what's the formula of the circle? Well, we had x squared plus y squared is equal to r squared. This is when it was in the 2D world. So now, when you looked at Cal 1, and you talked about circles, well, what did you do? You came and you took it from Cartesian coordinates and you put it into polar coordinates, which is very, very similar. But it's kind of ugly. So bear with me. It's going to be in the R3 world. The points are given by rho, theta, and phi. I can never draw phi. I won't make curly phi or phi. There, I'll make that red. I can't do cursive Greek. So the points are now given by rho, theta, and phi. Theta is going to be the normal theta that you guys are used to. Phi is going to be the distance from the origin. Similar to r, but a little bit different. So we're going to say rho is going to be the distance from the origin. That's what origin rate. Theta is going to be our normal theta. So we'll say normal theta. Incremental theta, right? Okay.
So it's still with respect to the x-axis, like.
Yeah. And then B is going to be the angle between the positive z axis and the vector to the point. And I'll show you what I mean. So we're going to have a 3D graph. We're going to look at the positive z-axis, and you say, look, everything below here, we're not going to look. We're gonna say it's gonna be the distance from the positive z axis, and we're gonna have a point on the positive z axis. And we're going to say it's gonna be everything that's positive, nothing negative. We're not gonna restrict it, but we're gonna use it as a basis to create a spherical coordinates. Because one thing we probably don't want is we don't want it to dive into negative numbers because then it gets a little kooky. That's where you'll go into differential geometry and you'll see more of it. What we're gonna do is we're gonna specifically have these coordinates just for our integration. So we're not gonna use this till much later in the class. Yes.
So you could say theta is the distance, or theta is the angle from the positive x-axis to the vector between the origin and the point, and then B is the angle from the positive z-axis to the vector between the points. Phi is the same as theta, except 2 z-axis instead of x.
Exactly. I like that definition. So we're gonna say is gonna be the angle between the positive z axis and the vector to the point. So the way that's going to look is this. Suppose we have some x hat. Theta is going to be this guy right there. Exactly what Brian was setting up for us. This is going to be our x. This is going to be our y. This bad boy is going to be our z. Now we're going to have rho, which is going to be this guy right here. We're going to have a specific point. And then from the point to the positive z-axis, this is where phi is going to be.
So that line is the projection onto the xy plane of the actual vector.
Yes. It looks like that. Hopefully that's easy for you guys to visualize. It's easier when we have this visualization, but it's hard when you can't really draw it properly. This is where the world of projections becomes so important. Then we can use those projections for when we're doing our optimizations and all those cool shell methods and washer methods that you've seen before, that you know and love.
Is the phi, is the arrow pointing the wrong way on that? I know it's fairly matters. Is it from the z-axis to the vector, or is it the other way?
Either way works.
Okay.
Just like
I
when
don't
it
know if
comes
it
to,
affects positive versus negative.
oh, I see what you're saying. All right, let's see. Yeah, it should be this way then. Yeah.
So opposite of going to.
This is what we're going to use our spherical coordinates for. All right, let's see. I have faith in you guys. Try to visualize. Let's say, for example, that's going to be rho is equal to 7. So if we have rho is equal to 7, of course we know we're going to have an amazing shape up here.
And everything else is just in that case. In this example. like theta.
Oh, I see what you're saying, theta and B. So let's say. Yeah, let's do that. If we have B is equal to 7, we know we're gonna have a nice sphere here, right? That means it's going to probably some right like that. Breath of the Wild. And let's say since it's gonna be origin, because it has to come from origin, we're gonna have a sphere that looks better than this on our page. And then if we do this, I believe you guys can already visualize what's going to happen. No. That's just going to be a 1 inside of a 1.
It's gonna be a sphere inside of the,
Inside of another sphere, right?
yes. Except like there's nothing.
There's nothing in the middle, so let's try to, actually, maybe I can show it better this way.
Kind of like the donut shape from earlier that's been rotated around, right?
Yes.
It's missing the core of it.
I don't know what. How to describe it.
It's like
It's a hollow sphere.
yeah, it's like Earth.
Yeah.
Right, the core.
Okay.
It's avocado.
Yeah, we got it. So we'll make this the outskirts of it. It's missing a portion inside there. Bigger sphere, maybe? That. I think that's a better drawing. So it's like when you look at your earth science books or your history books or whatever books that has the earth inside of it, and showing you the inside of the core. And like, oh, this is the inside of the core. This is the outer layer of the core. Like that. We're gonna use this much later in the class. And when I say much later in the class, I mean about middle of November. That's when we'll start using these stuff and playing with it. But for now, it's good to see it. Because then I think the homework is gonna ask you to visualize it, and it's good to visualize these. The good thing about the homework is you get a few chances, so if you get it wrong, you just redo the problem and get the credit. So it'll help you use trial and error for that section. That section is annoying. When I was going through it myself, I was like, I feel bad for them. Yeah, it's just, it's something that us mathematicians like to use. We'll say graph utilities for. It's just disgusting. Doing this by hand, like, if you look at textbooks from like the 20s and the 30s, like they hired artists to do it for them. That's how bad it was for us in that position. I don't know about you guys, I suck at drawing. Who could draw out there? Anyone an artist? Yeah. We're not artists. So we had to hire artists to do it for us. All right. Now, we're gonna start talking about vector value functions. The reason why we're gonna talk about vector value functions is now what we're gonna end up doing, we're gonna take these ideas that we had before, we're gonna vectorize them, and we're gonna start applying our calculus. So we're gonna have to recall how to take a limit, we're gonna have to recall how to do a derivative, how to do an integral. All of this is coming back. So this is the part where I need you guys, after the exam, email me, say, hey, professor, I forgot how to take a limit. Hey, professor, I forgot how to do a derivative. Hey, professor, I forgot how to do an integral. Trust me, we forget. We all forget. Like, it's, if you're not doing it, you lose it. Like, yes, sir.
I was gonna say, was that the end of the cylinder stuff, when we have the next chapter?
Oh, no, we're still looking at the cylinder stuff, but now we have to do vector value functions to, yeah, because I think that chapter, the way they had that chapter structured, like, oh, here's a formula of an ellipse, try to apply it to this. Now, if they're actually doing the vector value function way, it'll be easier to do all that math.
Just trying to stay organized on.
Oh, yes, of course,
separating stuff.
Yeah, yes, don't worry. If you guys are following along with the book is kind of doesn't do justice. It's nasty. I was looking at it. Basically, I was a can last night. I'm sorry. Yeah, I was just there. I was like, so it helped me release some demons for lack of a better word. Yeah. So, yeah, let's talk about vector value function. So this is going to tie into chapter 14. I'm going to use 14 as a basis to look back at, I believe it was 13.6. We're going to look at vector value function. So what's the first thing that you see and you should expect?
Vectors.
Vectors, because it says vector value functions. But you've been looking at vectors this entire time. We have a formula when it comes to just a specific line. What is that formula? Well, it's going to be the point plus some linear combination times the actual vector. And one way, one way we're going to look at it is this way. In R2, excuse me. Xi, Yj. In R3, we're going to have xi plus yj not equal plus zk. This is what we've been using this entire time. We can use I and j. IJK notation for everything. So what we're going to do is we can easily go from both of these guys. We can easily play around with those things. So basically what we have is IJK, just your x, y, and z coordinates. X, y, and z coordinates is just your we'll say your vectors that we've been looking at this entire time. So here's an example. I really like this example. It's basically RT is equal to we're going to have T squared I plus what is that T minus 1j plus 8ck. I know you guys can already do something as simple as this. Let's see. I like this one. R is equal to 3, what do we get? Well, we're gonna get 3 squared. 3 squared is 17, right? I'm gonna take 3 and subtract it by 1, which is what, 7. Then I'm gonna take 3 and times it by 8, which is gonna give us 104, right? We're used to this, right? We're used to doing this amazing math. And if we say R0, well, what happens here? Just negative j. And we already know how to put that into a vector form. Well, we're just gonna take the components, that's just gonna be 9, 2, 24. Because the I is gonna be our x, the j is gonna be our y, and the z is going to be our y. And the same thing for the next one. Next one, we can put this in a vectorized form. That's just gonna be 0, 1, and 0, right? And we can say to ourselves, oh, well, we know this. This is very similar to this guy right here. We already know how to work with this guy. So we can use either one to figure out our problems. Whichever is easier for you guys. I would suggest this one because it's the easiest. But if you're, let's say, business inclined, you can use that one as well. Because we use IJK notation at world. All right. So what we're going to say is this. X of t, y of t, z of t. We've been working with that since I think 2 weeks ago. You're probably saying to yourself, calculus 3 is still a 3 so far. Of course, it's going to get harder, but if you think about it, Cal 2, this is what I tell my students, Cal 2 makes and breaks you. Like all those integrals that you're working with, all those infinite sums, all those infinite things, we're going to do it again. But you're going to be so, we'll say, skilled in it, it's going to be easier. If you found Cal 2 hard, that's okay, because everyone finds it hard. Cal 3 is going to reinforce those ideas that you had before. Let's say you haven't taken Cal 2 in a while, that's okay. Those things are going to come back to you. It's, think of it like training rules. So one thing that I always tell my students is this. The struggles that you did before help you if you continue in the actual particular like discipline. Like I think everyone that fails Cal 2 can still become a mathematician. You just gotta maybe take the class a second time, they'll click, and then they'll just become that great. One of my colleagues that I worked with in New York, let's see what happened to her. Oh, well, she came from the Caribbean, and she didn't have this like extensive background in education or background in math. So I'm gonna go back to college, I want to study math. She just liked doing that. She started at the lowest level math you could have at any college, started with a remedial class. 6 years later, she was finishing up her master's. So she just had this enlightenment that one day that she sat I think in the admissions office. She said, I just want to study math. And she just built herself up. Now she's teaching, which she's at Lehman College in New York. So she can do it. I believe anybody can do it. You just gotta apply yourself. All right. We're gonna look at this guy right here. This guy is a vector value function. for the past, was it 2 weeks you've been working with this formula? We've been working with vector value functions. And we're gonna see that now we can apply all the known math that we know already. Take integrals, we can take limits, we can take derivatives. We're gonna use that forever coming back. Now, you guys missed it, but it's finally here. Here's an example. And you guys can do this example in a heartbeat. Find a function. Also, it's a good thing that I take your Pearson questions and put them in your exam. Because guess what will not appear on your exam? Those truths that you guys love so much, they won't appear because they're not in Pearson. So we want to find the function RT. I'm sorry?
What about the
Yeah.
random count two
Yeah,
question?
please don't spring the.
Oh, the random count two
Those
questions.
are-
Okay. Alright, when I make the test,
Yeah,
I can weed out what I don't want. So I'll make sure that there is at least one random count two question. Okay.
If you look at the, when you're reading the practice, just, like, say, like, everything from chapter 12 or to like.
I didn't have to pick, I just, I closed my eyes and went click, 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 that's what I did. So if something from count two appeared, I apologize and correct it. Does something from count two appear?
I haven't gotten through all of it yet.
We've gone, I've gone.
So if you looked at it, maybe you looked at like 2 questions, right?
I started it, sorry.
You had the intention of finishing it tonight, so okay, I'm ready. How much?
Two. No. Three.
You did 3, okay, that's good. I think how many questions on that, 35?
It was like 40.
Yeah, we're getting there.
Okay,
Okay.
yeah, so did I also put that timed or untimed?
It was on time.
I should have timed it. So it felt like a real exam. And then you have multiple attempts, so you can just, And I think if I put a time, and you click out of it, it stops the time. And then when you click back into it, it starts the timer again.
I see.
So it's like, of course, you're not gonna finish it in one sitting. It's just a practice exam, but if you stop it, you come back to it. It's okay, right? Alright, so we're gonna find the function RT passing through. We'll say A is gonna be the origin. And B is going to be 7, 8, and -9. So find me RT. You guys should be able to do this in a heartbeat. Excuse me. Oh, let's talk about the schedule. So we're gonna have test on that Thursday, gonna have class that day, which is 28th, we're gonna have class on the 30th. And I believe it's at the 5th, there's no class, right?
I mean,
There's no class. No class on the 5th, okay. And on the 7th, I'm gonna be in Comic-Con. So what I'm gonna do is, I'll probably make a video over this weekend. So you can have for the 7th. So you guys won't come to class, but you'll still have class, because there'll be a video. The video, I'll probably make it like an hour long, not 2 hours. Who wants to sit there for 2 hours long and watch a video? Mr. Derek, Mr. Ryan. Yeah. But I believe you guys sat there for like 2 hours and saw a video. So, yeah, I don't mind making a 2-hour video. I think if I make just an hour and focus on like maybe examples and examples and examples, you guys can find that. Alright.
what state is? I don't know.
Oh, New York.
It's in New York?
Yeah, this,
Not too bad, though.
yeah, this will take us on sale if you guys wanna join.
So we'll all be watching the video, of course.
Oh, yes, yes. Oh, that's right,
Right, yeah, of
yeah, you can't go because you'll be too busy studying and stuff.
course.
Yeah, over last weekend, there was, Philosophon East, anyone know about Philosophon East? Well, it's basically, it's a comic book, it's an anime convention, so I was at that, I'm sorry?
So is that in Ohio or something?
No, that was in Kalahari, up north.
Oh,
Yeah, so, yeah, the resort in the Poconos, right there,
oh.
and that's where I live, I'm like 10 minutes out, away from Kalahari. And my friend was like, oh, we're going to Philosophon, you coming, Jose? I was like, of course I'm coming. Oh, be careful. Oh, yeah. And I threw on some costumes and I was just walking around. And I felt out of place because everyone that was there, they said that their very first anime was, I believe, Attack on Titan. And Attack on Titan came out when I was graduating college. So I was like, yeah, like, yeah, we were like 6 when they came out. I was like, okay, I gotta go, guys. I'll see you later. So it was terrible. Yeah, they were too young. All right, but you guys can see this answer easily, right? It's gonna be what, 17, 18, and what?
You're 9.
Negative 19. And that's gonna be the vector. And if we want the function is just going to be 0, 0, 0 plus some t variable or some t of what? Should be 9, 8, and 9, 8, and no, 7, 8, and negative 9. Okay, sorry, I'm here, but not really here. It should be a vector, right? Did you all see that? Who didn't see that? Just checking. Okay, all right, perfect. Excellent. You guys are prepared for the exam. Everyone's getting at least a 70, right?
Okay, you said 70, that's.
Sound like we read
So
so
it's like me,
Do we have to show up?
Is it not 70?
Just show up again. No, ready, yeah.
No, no.
You guys are gonna get higher than 70. I'm sorry?
We're not sure.
You're not sure.
We'll study the
How much
Pearsons.
higher?
I'm sorry?
higher?
We'll study the Pearsons, the other ones.
You'll be fine. I think you're all gonna be fine. All right, here's the other example. We're gonna find an equation. Describing a line segment. From P is equal to 2, 3, 2, to Q, 1, 2. This one might require a little bit, algebra, but you should be able to do it. And whoever wants to put it on the board, let me know. was making eye contact. Scary. Mr. Mason? Yeah, I think. Let me try now. On the test, you can prepare. I have a faith you can do it. I don't. Similar, okay. What do you need for the line 7?
Distance between 2 points.
Distance between 2 points, right? We just want to set. When we find the equation, we plug in 0. What should we get back?
I mean, am I parameterizing this equation? You mean?
That's exactly what you do. Everything we were doing before is still going to be for a vector value function. You were doing vector value functions this entire time. I just never told you that they were vector value functions. Any questions? The only thing that Pearson will probably want you to do is this. R t is equal to 2 minus 1, or 2 minus t, comma 3 minus t, comma 2 minus t. Yeah, you could on the pencil. So we'll just. Drawing over to the bed. I think Pearson probably wants to do it. Other than that, you did perfect. Any questions about that? We've been doing every, we'll say, every class time for the past 2 weeks. Exactly what they want. Exactly what we've been doing. This is a vector value function. All right. Any questions before we move on? No, right? Simple. Cool. Like I was saying before, talk about the line, talk about the line segment. Now we're going to talk about the circle and the ellipse. Before we talk about the, let's say, circle and ellipse in the 3D world, let's try to remember it back from the 2D. In the 2D world, you have a circle, And then we also have an ellipse. And in the rule of the circle, we know that just with x minus k squared plus what? Y minus h, I think they usually do, squared is equal to r squared. And these two center points are equal, and we can center it at the origin. We just get x squared plus y squared is equal to r squared. Now when we're talking about an ellipse. Now remember the general form of an ellipse?
Squared over a squared.
Oh, yes, it was always equal to a specific value. What is that specific value? We usually always had it equal to 1. And then we had same exact thing, which was x minus k squared over some a squared plus y minus h squared over b squared. Am I ringing the bell now, guys? This was the general form of an ellipse. We always said it equal to 1, and we divided it by the two, we'll say, horizontal stretch and vertical compress, or vertical stretch, horizontal compress. So we have two different ellipses. One is this direction, and then the other one is that direction. The cool thing is, when we're talking about these two things right here, if those that took physics class, remember Kepler's laws? The law of areas. Okay, that's fine. Well, Kepler's laws. Basically, Kepler had 3 laws, and independently and mysteriously, Newton had 3 laws also, right? Wayne? Yeah. Basically, what Newton did was he took Kepler's laws and he brought it into the world of calculus, because Kepler was nothing but algebra. So then Newton and we'll say loosely invented calculus at the same time that Leibniz did, and did what he did. Some people say that Newton copied from everybody, and other people say he's completely original. So there's two different worlds of which one you want to believe. So, excuse me. We're going to have to take these ideas and put them in the 3D world. And you guys should already have an idea of how to do it. Does anyone have an idea how to do it?
I mean, my first thought would be to add C coordinates.
Okay, I like that idea.
Yeah.
C coordinate. And we're gonna have, well, we're gonna have our axis in the
Well, I mean, could, for a circle or wait, this is for sphere, are we starting with that, or?
Yeah.
Okay. Yeah, I mean, my thought would be the same x minus k squared thing, adding in z term for the center and have it be rho for the radius c kind of thing.
Perfect, I like it. So, if we're gonna take, we take a circle, and we know we have r cosine of theta, right? And we know we have y is equal to r sine theta. This is our polar form of it. Now, what we're going to do is, we're going to vectorize it. We're gonna have r cosine theta and r sine theta. Just like what we've been doing for components. And then what we can eventually do is this. We can say What can we make it? Oh, let's do a fun example first. This fun example, let's say RT is equal to 2 cosine of t and 2 sine of t. And we'll say for t is in, we'll say 0 and 2 pi. You guys already know these look like that. Well, what's our R value in this case? 2. That means we're just gonna have a circle as big as what? 2, right? Yep. Bad circle, but
It was pretty good. Pretty good. Like 3/4. It started out good.
yeah,
If you
it
just
was-
move the axis around, it's like, it is circular.
but if it was a perfect circle, that would be kind of scary, right?
It would.
I don't know that. Like the high school that I work, you have you have another teacher that's obtained her PhD. So her name is Veronica Murphy, Dr. Murphy, and all the students are like, she can draw a perfect circle. I was like, you guys really accept that? And they're like, yeah, it's a perfect circle. I'm like, you guys know that when someone draws a perfect circle, they're clinically insane. She's like, well, she's kind of crazy. So I'm like, all right, she's kind of crazy. Pretty cool. All right. And I said to them, am I crazy? They're like, no, you're not as crazy as she is. I was like, okay, all right, I guess I'm not as crazy as she is. So what we're going to do is this. We're gonna now say our general form for a circle is just going to be RT is equal to R cosine of t, R sine of t. And of course, we're going to restrict our axes just because we can do that. Now this is where it becomes a little bit fun. So that's the general form in polar coordinates for a circle. What do we think is a general form for an ellipse? What do we do with an ellipse? An ellipse, we're not going to have these perfect numbers where they're both the same, right? Well, what's going to happen is we're going to have one's going to be a small number, and the other one's going to be a big number or a bigger number. So what we're going to eventually have is we'll have something like this. So just RT is equal to maybe 2 cosine of t, comma 3 sine of t. And of course, we'll still have it in the same interval. Like we did before, we divided each iteration by A or B. We did the same thing. We're going to have the same exact thing. But what are we going to do for our primary numbers? There's going to be the coefficients of the amazing ellipse. For the general form, maybe I'll put general form of ellipse. Circle. That's just going to be R of t is equal to A cosine of t, comma B sine of t. But then the vector form. And of course, we're going to restrict this from 0 to 2 pi. Everything that we've been doing since trig class. Now we're just giving it a fancier form in the form of a vector. Any questions so far? Easy stuff. So one other thing that we're gonna talk about before I give you the polarized version of the 3D graph. Well, these vector value functions are gonna be plane curves. When it comes to plane curves, we can have it look like this. Which we see in patterns. And this right here is going to be a vector value function. What are we concerned with vector value function? Direction and magnitude. So of course, when you look at this, the first thing you think to yourself is, Professor, what the beep are you talking about? That's not a function. We're talking about vector value functions, so we're more concerned about the direction, its magnitude, rather than the normal vertical line test that we're used to looking at. But we're going to be using this for our vector value functions. These plane curves are still going to exist. These plane curves are still going to be a function. It's still going to we'll say violate the function idea that you guys are used to, but we're going to say, okay, this is going to be a vector value function. So take that idea as a function that you had before and keep it in the world of Cal 1 and Cal 2. I think your professor went over this in Cal 1 and 2, right? Something close to it.
It doesn't seem totally us.
Okay, alright. Okay, and I think it was Eric, right? I never asked Eric what he did for you guys, which is okay. I like to do my own thing. All we're going to do with this, we're going to take it into the 3D world, and we're going to have the same exact thing. And we're just going to call this guy a space curve. This is going to be an R3, and this guy's an R2. So the same thing is appearing, now we just call it a space curve. And as you guys guessed, what we're going to do is we're just going to take the actual thing and have two sides of make the cosine first. To cosine of t, to sine of t, and t itself. If you remember correctly, what we're going to have when it comes to this is just circle. This is the last idea we're going to have, and probably talk about a little bit in end class here on this note. Try to picture how that guy is going to look.
I mean, it depends on where T is restricted to, but
Depends on where T is restricted to. So let's get funky. Let's do this. Let's say T is going to go to infinity. How do you think this function is going to look? You're probably thinking of restrictions. You're thinking of it in terms of this. Well, what am I doing to this thing? What's happening to this thing? Spinning around, right? I'm going 0 to 2 pi. Technically, can't I go beyond 2 pi? I can keep going. I can keep going. But what's going to happen in the 3D world is what? You're going to keep going, right?
Yes.
And you keep going and you keep rising, what happens?
you wouldn't have like a cylinder, you would have.
You'll have a slinky. You'll keep going, keep going, keep going, keep going. Because what is it doing? Well, it's rotating because we know that we have to draw. So when we keep drawing it, once we get to 2 pi, well, we're going to continue, right? We're going to keep continuing. So we can think of it like they told you in Cal 1 when it came to limits. Well, if the limit doesn't exist, you basically, you pull your pen off. Oh, wait, it has a break in the graph. Does the limit exist? What's happening here? We're doing the same exact idea. Now we're going to keep spiraling and spiraling. And we're going to say to ourselves, well, when do we pull off? What do we create? Oh, we pull off. Now we have a discontinuous graph. Now guess what we can start talking about? Limits. We're going to say, oh, what is the limit of this function? We're going to see that when we draw this guy, excuse me. Where we're going to draw this, we're just going to take in this is X, this is Y, so we're going to take it like that. And it's going to start to go like this, like this forever. Because T keeps blowing up. Now we get this nice, cool, slinky. I think this is spelled slinky, right? Did anyone have a slinky when they were younger? I think we all did. I even had to skip it. You guys know skip it? Oh, you know skip it. Yeah. Had a cool commercial and everything. Yes, we're going to create this slinky effect. And now we're going to start talking about limits. And once we start talking about limits, we're going to start talking about derivatives. We start talking about derivatives, we're going to start talking about anti-derivatives. And once we start talking about that, then we can bring in the shell method, the washer method, all these old things that you remember from before. Then we can go deeper into the actual calculus of it. Then we can start talking about related rates and optimization. It's basically going to be Cal 1 over again. And after we finish all that, then we're going to start talking about Cal 2. What did you guys start off with Cal 2? Did you probably start off with arc length, or was it the last thing you did Cal 1?
I think it was Cal 1.
Cal 1. You said you did arc length in Cal 1. You did shells, I think, and washers in Cal 2, right?
One of the two, yeah.
Okay.
We did Cal 1, Cal 2.
Yeah. Okay.
I know what you're talking about.
Yeah, that's what our progression is going to be. Basically, Cal 1 or 2 again, just now in 3 dimensions.
So, okay, I was gonna say, so it's taking all the stuff we did in Cal 1 and 2 and just expanding to 3.
Exactly. And then, I don't think we can get to the n dimension. I think n dimension, I'll leave that for your real analysis professor, if anyone's going to take real analysis. but. I think the only person that's gonna take real analysis in this class is gonna be me, because everyone else is an engineer or a physicist or a biomedical engineer. And real analysis, basically, real analysis starts off with just focusing on sequences and series. And then when you do sequences and series, you go into derivatives, and you do the actual delta epsilon proofs that you've seen in normal Cal 1, but this one's on steroids. And
Already on steroids, what do you mean?
oh, I'm sorry. Well, no, delta epsilon proof is like it's easy. You just do some scratch work and okay. I mean, maybe I might. Yeah, and then after you do the delta epsilon proofs, then you go into integration. You do the actual integration of real analysis, and then they say, oh, guess what? This was all in just one dimension, or not, 2 dimensions. There's all in just 2 dimensions. Now there's n dimensions. You do real analysis 2, which is just taking everything you learned in real analysis 1 and bringing it to n dimensions. And then after that, you take something called real analysis 3, which is a graduate level course, and you do something called the Lebesgue integral. Those of you that are studying engineers, if you're studying engineering, physics, real analysis 3 might be your best bet, because Lebesgue integrals are better than Riemann integrals. Riemann integrals look at the area underneath the curve in the x direction. So when you look at the curve, you have some specific curve. You look at everything in the x direction. The Lebesgue integral is more intuitive. You look at everything in the dependent axis, the y-axis. It becomes easier. Actually, I'm lying to you. It becomes harder, but easier intuitively. So there's a lot of integrals that is Riemann integrable, but not Lebesgue integrable. And there's a lot of Lebesgue integrals that are not Riemann integrable, and they're a lot more prettier and fun to work with. And that's something that you'll use in the, well, I'll say maybe aerospace engineering. So if you're going to go to aerospace engineering, I think your best bet to take a real analysis 3 course just to see what's going on with Lebesgue. End class on that note. Any questions at all? So I have questions along the lines of, hey, what's on the test?
No, what are you for the test? Will you count the answers in Pearson, just the answer in Pearson or answer in Pearson, and maybe if you got it wrong, it's great also by your work as well.
Oh, I want you guys to kind of work.
Okay.
Because I want to look at the work, because hey, you typed in the wrong answer by mistake. But you wrote it down the right way, but you just were so nervous because it was a bad test day and you just typed in the wrong. I'll be forgiven.
Okay.
Because that makes no sense. That, hey, with all this work, you wrote down the right answer, but you transferred it to the computer, you got it wrong.
All right. That was my question.
All right, we'll end the recording here.
I actually got until 25, so we got stuck on 2 of them.
Okay, let me just stop this recording.